Welcome back. Recently, we solved absolute value inequalities algebraically, where we split our absolute value into essentially two different inequalities and solved each, and then you applied the and or and matched them up. Now we are going to use the graphing method. So in this video, we're going to solve absolute value inequalities by graphing. So recall that the absolute value is the distance between the graph of a number and the origin on a number line. And I said that the origin is not always 0. And that's going to be really important for us here as we determine where the origin is and then take the distance from that origin, and then we're easily able to graph our absolute value inequality and figure out its algebraic solution. So we talked about absolute value being distance, and here in these three examples we have like the distance is exactly 3 units, the distance from some origin, or the distance from some origin is greater than 3 units, or in this final one the distance from the origin is less than 3 units, and our origin is 0 in each one of these. So, and we also talked about conjunctions, and we talked about a conjunction is the distance is less than something. So the distance from the origin is less than. So that means if the distance is less than some value here, c, that means we're going to move closer to the origin. We're going to go some distance and away from the origin, and then we're going to move closer to the origin. Okay, because the distance is less than some value. In a disjunction, the distance is greater than some value. So we're gonna go from our origin, then we're going to move some distance greater than that, and all those values that are farther away will be will satisfy the inequality. So this distance business, the distance is greater than, or the distance is greater than, or the distance is less than, is going to be very important for us. So let's take a look at standard form of an absolute value. When I talk about standard form, we have a couple things going on. Everything is cleared away from the absolute value of ours. Also in standard form, our coefficient on our variable, in this case x, is 1. Okay, so standard form, the absolute value of ours are clean. Okay, in standard form, the coefficient on our variable is 1. Okay, and we can have standard form, this is an equality or an equation, but we can have standard form on an inequality like x minus a is less than b, or we could have, x minus a is greater than or equal to b. This is all standard form because everything's cleared away, our coefficient is 1. Okay, I'm not going to worry too much about whether it's less than or greater than and determining whether it's standard form or not. Okay, but in standard form, we can easily find our origin. Our origin is the opposite of the sign that we're looking at here. So really, our origin here is a positive a. Okay, so if we had, the absolute value of x plus a is less than b, that's standard form. That's like x minus a minus a is less than b. So in this case, our origin is negative a, or the opposite of a. Okay, so that's something to keep in mind. Our origin is essentially the opposite of what we're looking at here. And then our distance from the origin, is exactly b. Okay, or in this case, our distance from the origin would be less than b. And it's really important that when you're telling me what the distance from the origin is, that you include the equal sign or the inequality. Because our distance, the fact that it's more than whatever the value of b is, or less than the value of b, that's important. Okay, if you just put b, then it's exactly that, but that's not going to necessarily be the case. Let's take a look at our process. Our process for solving absolute value inequalities by the graphing method, we want to rewrite our absolute value into standard form. So we want to isolate the absolute value bars. We want to strip everything away. We want to clear that first. So that's going to be the first thing we do. Okay, strip first. Use reverse order of operations to clear everything away from the absolute value bars. Okay, again, I discourage distributing into the absolute value. And then watch out when you multiply or divide by -1. This second part is where things get a little tricky. We want to make sure that the coefficient on the variable is exactly 1. Okay, so if it's not 1, if we have something like the absolute value of 2x minus 5 is greater than 3, well, this is not standard form, so we'll have to factor out the absolute value of 2. So if we factored out the absolute value of 2, we'd have the absolute value of 2 times the absolute value of x minus 5/2 is greater than 3. So here we have factored out the absolute value of 2. And that's how, if we distribute it back in, we would get the same thing. So I know I've done that. Okay, so that's the tricky part. You might have to factor out the absolute value of the coefficient on x. Then we would apply the absolute value. So the absolute value of 2 here is just 2. And then we would divide both sides by 2. Then we would determine the origin. So it's the opposite of the constant inside the absolute value. So in this case, my origin would be a positive 5/2. And then we would determine the distance from the origin. Well, if I divided all this by 2, I'd get x minus 5/2 is greater than 3/2. So my distance from the origin in my example here is greater than 3/2. And then we would graph and then write our algebraic solution. So if I were to graph this, okay, where my origin is 5/2, well, just put that in as 5/2, and my distance is greater than 3/2 away. Well, 5/2 plus 3/2 is 8/2, or 4. And I have to subtract 3/2, which is 2/2, or 1. And I want my distance from there to be greater than 3/2. So all those points to the right of 4 are greater than 3/2 away from my origin, and all those points to the left of 1, not inclusive, all those are greater than 3/2 away. So that's my graphing solution. And then I would write my solution using interval notation. So I'm going from -infinity to 1, non-inclusive, in union with 4, all the way to positive infinity. So there would be my algebraic solution using interval notation. So let's do some sample problems. Some of these start fairly straightforward. So everything is stripped away here in A from our absolute value bar. So we get the absolute value of x plus 7 is less than or equal to 4. So our origin is just the opposite of this. So our origin here is -7. And our distance from the origin, here's our distance, is less than or equal to 4 units away. So -7 is our origin. I need points that are 4 units away, so 4 units to the right. So -3 and -11 are 4 units away. And I want all the points that are less than or equal to 4 units away. Well, all of these points in the middle here, these are all less than 4 units away from our origin of -7. So our algebraic solution is all the points between the -11 on the low end and -3 on the high end, inclusive. Our second problem, 2 times the absolute value of x minus 4 plus 11 is greater than 17. So we want to clear everything away from the absolute value bars. I'm going to subtract 11. So I get 2 times the absolute value of x minus 4 is greater than 6. I'm going to divide by 2. And I get the absolute value of x minus 4 is greater than 3. So my origin is the opposite of -4 or +4. My distance from the origin, let's talk about that origin real quick. Standard form is x minus something. Isn't that x minus a +4? So my origin is the +4 because minus is the standard form. And the distance from the origin, we want everything that's more than 3 units away from 4. So I'm going to start with 4 in the middle because that's my origin. I need 3 units to the right, so that's 7. 3 units to the left is 1. I want all the points that are more than 3 units away. So I'm going to use the parentheses because I'm not going to include exactly 3 units. So everything to the right of 7 and everything to the left of 1. So our algebraic solution, -infinity to 1, not including 1, in union with 7 to +infinity. And our final sample problem, something that's a little bit more complicated. Again, we've got to strip everything away. So we have 21 minus 4 times the absolute value of -3x plus 2 is greater than 5. So I'm going to subtract 21 from both sides. We get -4 times the absolute value of -3x plus 2 is greater than -16. I'm going to divide by -4. So that should tell me to change the direction of the inequality. So I get the absolute value of -3x plus 2 is less than 4. Change the direction. Now I need to factor out the absolute value of -3. So I'm going to factor that out and write that up here. So I have the absolute value of -3 times the absolute value of x minus 2/3, because that changed my sign. I factored a -3 out of there. So if I distributed that back in, I would get my same result. That's still less than 4. Now my instructions say to take the absolute value of -3. So I have 3 times the absolute value of x minus 2/3 is less than 4. Now I have to divide by 3 because I don't have everything stripped away. So I have the absolute value of x minus 2/3 is less than 4/3. Now, finally, I'm in standard form. So my origin is the opposite of what I'm looking at here. Okay, so I need the opposite of this. So my origin is a positive 2/3. And my distance from the origin is less than 4/3. And again, just a reminder, that's really important that you've got that inequality symbol there. And now we go ahead and graph this. So my origin is 2/3. I need things that are 4/3 away, so 2/3 and 4/3 is 6/3 or 2, and 2/3 away, or pardon me, 4/3 away would be a negative 2/3, and I want things that are less than that, so all these points are less than 4/3 away from my origin. So all these points satisfy my absolute value inequality because they're less than 4/3 away. Just redraw that, 4/3 away from my origin. And then finally, my algebraic solution. Well, those are all the points, not inclusive of negative 2/3, 2, 2, and non-inclusive. So there's my algebraic solution in interval notation. So there's your introduction to solving absolute value inequalities by the graphing method, some fairly complicated sample problems, and we'll do some more practice when I see you in class.